Have you ever wondered about how guardrails work? You see them everywhere on almost every highway in the United States, but let's take a closer look into them. Firstly, take a look at how this guardrail works. The car crashes into the guardrail and almost dents it while being reversed back on course. This allows the guardrail to apply more friction onto the car and is part of the design. Let's take a closer look. Upon impact, the guardrail is meant to cushion the car by denting. However, to avoid breaking, it is corrugated in order to strengthen the structure of the guardrail. But how is this scientifically effective? And how is science applied, and especially physics, applied into this? Let's take a look into Newton's laws. Firstly, the law of inertia, or the first law of motion. Any object has a tendency to persist in its current state of motion until an external force has been acted upon it to change its net force. This means that upon impact, the car will decelerate rather than actually stopping immediately, as it has an inertia, which is to have a tendency to remain in its current state of motion. This is why the guardrail slows it down. In this case, the external force is the friction being applied by the guardrail. In this case, it's the kinetic friction. But how does kinetic friction work? Well, let's take a look. As we can see here, the formula of the kinetic friction is Fk equals mu k times eta. In other words, friction, or kinetic friction in this case, is equal to mu k, which is a coefficient of friction, times by the normal force, which in this case is used by the Greek letter eta. Now, to find out what really is the common case here, is we have to find out what the average weight of cars is, which is in kilograms. In this case, it's 1,850 kg. Furthermore, as you can see in the video, we use this to find out the normal force, as once we multiply it by the gravitational force, it gives us the force being acted upon the car downwards, which is the gravitational force, which is equal to the mass mg, which is 1,850 kg in this case, times it by 9.81. Now that gives us the normal force, as it is equivalent to the gravitational force. Then to find out the friction, it will require us to have an example. For example, we will have to have the coefficient of friction to be set. We cannot know what it is, as we only know the normal force in the formula, and we do not know any other of the two variables. Furthermore, the coefficient of friction itself, the normal force itself, depends on the angle at which it is hit. This is used by cosine, which is cosine theta, theta being the angle at which it comes upon impact with the other surface. In this case, the angle between the guardrail and the car, which will require another example. Let's say, for example, if we have a coefficient force of 0.4, or coefficient of friction force, or kinetic friction force 0.4, this would mean that once we multiply it by the normal force, we would get our frictional kinetic frictional force, which is the answer. Now, what about Newton's third law? Every action has an equal and opposite reaction. In this case, of course, the action force is the actual force of the car, and the reaction force is the force being reapplied equally to the opposite direction by the guardrails. Let's take a look in this example. In this example, as the car approaches the guardrail, it is being pushed back equally to the opposite direction, which it is applying the force, the same amount of newtons. This forces the car to turn backwards, as combined with the force of friction, the car's force cannot be sustained. But those aren't the only factors to be taken into account, as guardrails have another mechanism working into them. For example, upon impact, as you can see in this video, it dents
and forces the car to at least decelerate at a much faster rate due to the fact that there is a larger surface area opposing the vehicle. As you can see right now, the bus is curving and somewhat opposing the guardrail in an opposite direction as it moves. This changes its direction as a vehicle, and which, as you can see, obviously changes its course back on track. This will minimize the damage to the vehicle, which is also part of the mechanism of the guardrail. Furthermore, as you can see here, the terminals of the guardrail are designed to, in a way with the strong posts, that the vehicle will not go through, the guardrails will not go through the crumple zone and damage the driver or passengers themselves. Furthermore, corrugations within the guardrail strengthen them, and as you can see here, from a bird's eye view of the crash test, will eventually minimize the denting of the guardrail so as to prevent the ultimate damage to the guardrail and braking.
But how effective is it? I believe it's pretty good actually. Well, I disagree. Let's take a look at the pros and cons. Sure thing. The pros are countless. Personally, I believe firstly that the fact that it doesn't require maintenance greatly conserves the labor and resources required to keep maintaining them, unlike roads and like road bumps or other road safety devices. A W-beam guardrail, which has been totally destroyed and requires replacement rather than repair, will cost about $1,900 for every 156 feet. That's amongst the cheapest safety devices. Yes, but on the topic of cheapness, haven't there also been frauds such as by Trinity Industries, which have changed the design of the end terminal, increasing the price of manufacturing by $2 each for each post, yet diminishing safety and increasing hazards? And while on the topic of safety, why don't we mention how it malfunctions and ends up in a process called slicing, where the terminal doesn't work, or the guardrail itself between the posts break, and then ends up slicing through the car and fatally injuring the driver. You seem to have a point. But then again, back on the pros, there are many new models being made to rectify this issue. For example, the Thri-beam is a much stronger version, and even the modified Thri-beam, rather than the G9 beam W-beam, may be a bit more expensive, but still drastically increases safety. On the topic of respecting the safety standards set by the state, new guardrails are being invented every year, such as the cable guardrails, and a totally different design, which is the rolling guardrails, which applies rolling friction, which helps save the car rather than destroy it at the same time. Speaking of which, the guardrail is designed to minimize the damage of the car, which is why there are different materials for different roads. For example, on roads without trucks, they will tend to use materials which are less durable, as the trucks will not require too much of an impact. This is again by Newton's second law, F equals ma. This is explained by the fact that the more the mass, the less the acceleration, but still it will increase the momentum, which means that the force and the impact will be much greater. Also, have you ever noticed, like most other road safety devices, such as road bumps, they're only on a short point of the road, they're only on a specific area of the road, whereas guardrails are designed to maximize safety across the whole entire highway, or on the bridge, or much larger distances, while it's not taking space, as it is only on the side of the road. True, but on the topic of not taking space, doesn't that mean that, and the fact that it's only on the sides of the road, doesn't that mean that all accidents that happen within the road are not are not under the protection of the guardrails? That's true, but there are other safety devices to compensate for that. Yes, but they're only mostly on highways and not on other areas. And in some rural areas, you don't find them in mountains. Furthermore, these things don't really work well on large vehicles, and large vehicles tend, although they decelerate quite quickly, they tend to tip over, such as trucks and buses.
And just a quick side note, more specifically above 32,000 pounds.
This is still fatal for the passengers, which means that guardrails do not take large vehicles into account. More specifically, around 33,000 pounds of mass, not weight, because weight is measured in newtons, and that's the mass multiplied by the gravity acceleration of Earth. You make a point, but engineers are advancing in technology every year, and are trying to create new designs to solve this.